Hi everyone again, and now we have Malte Tichy. Malte, and if I didn't pronounce your name right, please correct me. To talk about what could possibly go wrong with when evaluating forecasts. Malte, after he joined Blue Yonder as a data scientist in 2015, and he has worked on numerous external and internal projects, which all of them kind of involved in programming Python, evaluating predictions, and communicating the achieved results. So, and Monty, and you can start now. Thank you.
Yeah, thank you, Howard. Yeah, my name is Malte. I joined Blue Yonder in 2015, and one of the first questions I asked was, of course, what could possibly go wrong when evaluating forecasts? Now, 6 years later, I can hopefully give you partially an answer to that. So forecasts can concern continuous quantities like the temperature of tomorrow or the blood pressure, but they can also concern discrete categories, like will that email be marked as spam? Is that animal a cat or dog? In supply chain, what we are dealing with, we often have a hybrid case because we have discrete quantities of countable atomic objects, just like t-shirts. So this is a quantity because 0 is smaller than 1 is smaller than 2 and so on, but it's also discrete because we don't have 2.5 t-shirts or 3.7 t-shirts that we could sell. And this combination that we have a discrete quantity is actually offering us quite some challenges. So let's set up the stage that we're working in. Let's assume we are a data scientist and our task is to predict t-shirt sales in time. We are given this data set here, the t-shirt sales in the past. We're training a model, and we are then extrapolating our prediction to the future to make a forecast how many t-shirts will be sold. The future will eventually dribble in, and we have the actual out of sample sales. And management will come at some stage and ask, how good is that forecast? Now, how good is the forecast is a really hard question, and we like to substitute it with a much clearer question that is much better confined. For example, what's the forecast's mean absolute error? Here, we plug in the observations that we have, we plug in the predictions, and we get a number, and we can give that number to management. But management won't be happy with that. They want to know, what does it mean? Is this now good or is this bad? And we'll see that coming from that expression here to a judgment of a forecast is a really long journey. In the first place, we have to interpret our forecast wisely, because forecasts trivially are not observations, and it's not even so clear what number to plug in here as a prediction. In the second place, we will have to manage expectations. We have to have a different expectation for the slow sellers that sell maybe once or twice a day than from the fast sellers that sell 100 times a day. So we cannot compare the slow sellers to the fast sellers, and I'll show you why. Finally, there are many things that can go wrong when grouping data, and you might fall into the hindsight paradox where you think you should have known better, but it turns out you shouldn't. So let's start by interpreting the forecast wisely. Management might come to you and they might ask, what do you mean by tomorrow red t-shirt sales will be 9.47? Do you really mean we will sell 9 t-shirts and then somebody will buy half a t-shirt? Well, obviously not. This statement here is a probabilistic statement that reveals our belief about the mean sales that will occur on days like tomorrow, where we predict 9.47. And what is not in this statement here, but somewhere implicit, is we probably have done Poisson regression or some kind of regression that takes into account that we have a discrete quantity and there's a probability distribution behind the scenes. Now that probability distribution becomes important when we want to evaluate mean absolute error, where we subtract from each observation our prediction. Because the observation is pretty clear what we want to plug in. Say we observe 7 t-shirts, well, then we just plug in the number 7. But this here, that's not a number, that's a function. And if we want to summarize that function, we have to do this in a certain way. And it's not clear a priori how we would summarize a distribution to plug in here. And this summary is also called a point estimator. And this problem to find the correct point estimator to plug in into a metric, that's very generic. That will occur for every evaluation metric. Now, for this concrete case, let's assume we have this Poisson distribution rate 9.47. So we have one forecasted distribution, and it turns out that the point estimator for mean absolute error is the median of the distribution. So the correct number to go into this prediction K here, when we evaluate mean absolute error, is the median, so the number that divides the probability distribution into equal halves. If you evaluate mean squared error, then the correct point estimator turns out to be the mean of the distribution, so the most popular summary statistic, and the number that you would use is 9.47. If you use a more exotic and actually quite dangerous evaluation metric like mean absolute percentage error, the number that you have to plug in here is sometimes called the -1 median. I don't have an intuitive way to explain this, but it's the number K that solves this equation as well as possible. And now for this particular example, with that distribution here, the -1 median turns out to be 8. So for MAPE, our prediction would be 8. For the mean absolute error, the median that we plug in here is 9, and the mean is 9.47. So for mean squared error, we would use 9.47. Okay, now you might ask, well, these numbers are different, but they're not so different. Couldn't we just always summarize distributions by their mean? I mean, the mean is the most popular, the most intuitive summary of a distribution. Well, we could do that. This is what you would get here. You have, as a function of the true rate, the bias that you will have in your estimated rate if you used a naive MAPE estimator or naive MAE estimator and don't do this differentiation between mean and median. So for MAE, you will heavily underestimate the slow movers because you will predict 0 essentially everywhere whenever the article is selling more slowly than 0.7 times a day, and you will be quite inaccurate on the mid movers. For MAPE, you will heavily overestimate the slow movers because the lowest prediction that makes sense for MAPE is 1. And you will underestimate the mid to fast movers. Now note, this is all in the lab. This is all in an idealized case. So the answer is clearly no, because the best model that you will get will be biased and quite inaccurate. And now think about it. If we have a procedure that doesn't even work in the lab in a totally idealized environment, what could then happen if you're out there in the real world where you have many more problems to deal with? So far, we assumed a Poisson distribution, and I didn't really substantiate why that is a good choice. And you might also say, well, you know, I understand the concept of uncertainty. I know what uncertainty is, but I don't want uncertainty. I want a deterministic forecast. If the forecast is 5, the mean is 5, I want the number of sold t-shirts to be exactly 5, not 4, not 6, and then all these summaries will be the same number. Yeah, let's see what that actually means to have such a requirement on a forecast. Expressed as a probability distribution, we have this figure here. The probability to have 5 sales is 1. The probability to have 4 sales or 6 sales or 8 or so is just 0. So what does it mean about the degree of information that we have about our customers? Well, that means we know 5 customers of which we can say with certainty they will definitely buy a red t-shirt tomorrow. But not only is this a very strong statement about these 5 customers, I mean, who is ever so sure to buy a red t-shirt on the next day? But it's also a really strong statement about all the other customers, because we can absolutely exclude that nobody of them might spontaneously buy a red t-shirt. So this degree of certainty is unreachable if you have a product-based forecast. And already if you weaken the assumption a little bit, so you say you have 6 customers and each of them has a probability of 83% to buy the article, you get this binomial distribution here, which is immediately much wider. The probability to observe exactly 5 goes down to 40%. Now you can move on. You can think of 10 customers with probability 50% each. This might be the situation if you have a really small bakery in a really small village with very few customers, and each customer has a really high chance to come and buy bread in your bakery. Then you have this distribution like that. But typically for retailers, we don't even know how many customers will come on a given day. And we'll have to use the Poisson limit. That is, we somehow have many customers, and we have an estimate of what's the average probability for a customer to buy the product. So that is somehow the standard benchmark for integer predictions under certain assumptions, like many potential customers. Each customer has a very small probability to buy an item on average, and nobody buys 2 or more items. The Poisson distribution is parameterized by exactly one parameter, that's the rate, and the rate also coincides with the mean of the distribution. That's very convenient. That is the Poisson distribution for a rate of 1, for a rate of 4, and a rate of 12. Now we can plug the pieces together. We can now ask, what is the achievable relative mean absolute error under the Poisson distribution? So assuming we are correct, assuming our forecast is perfect, and the true sales are really distributed according to Poisson distribution, what is the mean absolute error or relative mean absolute error that we will reach? Because this is a lower bound to what we can promise to anyone, for example, to management. And that's really easy to do in Python. I mean, you just import the Poisson distribution from scipy stats. Let's generate a large array of possible Poisson rates between 0 and 15. And for each of these rates, we draw 10,000 observations that we randomly draw from the Poisson distribution. So we have a big rectangular array here. And we can then compute the achieved mean absolute error. So we take the mean over the absolute difference between the median of the rates. We've just seen that the correct point estimator for mean absolute error is the median, and we subtract the observations. And we have to choose the correct axis to do our mean. And if you do that, you will get some numerical results. There are also some analytical formulas that you can find in this paper, and you'll get a plot like that one. So as a function of the Poisson rate, as a function of our predicted rate, this is the mean absolute error that we can expect in the idealized case. So if the prediction is 5, we have to live with a mean absolute error of 1.75. And if the prediction is 10, we have to live with a mean absolute error of 2.5. Now, obviously, this curve is increasing, and sometimes what people do is they try to normalize this scaling effect away by just dividing by the mean observation. But this doesn't work, because then you get an inverse scaling effect in the relative mean absolute error. That is the mean absolute error divided by the mean observation. You have to, you just see that you have to live with high values for the slow sellers, and only if your prediction is large enough, you can expect the relative mean absolute error to be lower than a certain value. Now, when we show some scores of what we achieve for different products, we should always show them together with benchmarks. Now think we have different assortments. We have the dresses, we have the socks, we have the t-shirts, and we reach a certain relative mean absolute error that is 0.76 for t-shirts and is 0.55 for socks, and somewhere in between for the dresses. If you only see these bars here, your conclusion would be, well, the socks are doing best and the t-shirts are doing worst. But we just saw that what you can achieve depends on the prediction itself. So you should include the Poisson benchmark, the best possible that you can ever have. And now the conclusion is very different, because you see that for socks, there's a huge potential that could, in principle, reach a relative mean absolute error of only 6%. So there's a lot to gain here, while the t-shirts are already close to what is possible in principle. So, but why are slow sellers differing so much from fast sellers? Because it turns out that few is really different. In the first place, it's much harder to learn from slow sellers than from fast sellers. How much do we learn about a product by observing it on one day? Let's assume it's a red t-shirt, and the red t-shirt didn't sell at all. Nobody wanted to buy that red t-shirt. What can we say at the end of that day? Well, this blue curve here is the posterior distribution of our belief of the rate of sale of that t-shirt after having measured 0. So we have measured 0. The most probable value is that nobody ever wants to buy the t-shirt, but there's still a finite probability density that I have a rate of sale of maybe 1, and I was a little bit unlucky because nobody happened to buy the t-shirt. Maybe I even have a rate of sale of 3, and I was very unlucky that nobody bought the t-shirt. But so relatively speaking, there's quite little that I can say about the true rate of sale. It could be 0, it could be 0.1 or 1, or maybe even 4. And we have a strong dependence on our prior beliefs. So do I believe that t-shirts typically sell once a day, or do they typically sell 10 times a day? This is very different for fast sellers. I mean, consider blue socks. Everybody likes blue socks. So they sell 1,000 times on the first day we observe them. This is the posterior probability distribution for the rate, which is very peaked around a rate of 1,000. So you can be absolutely sure that the true rate is between, say, 800 and 1,200. It doesn't really matter whether you thought blue socks are popular or not. They sold 1,000 times. You can be sure that the true rate is close to 1,000. So we have a phenomenon here that the quantity of interest, the rate of sale that we want to learn, actually determines itself how fast we can learn about it. And this is why we are learning much less from the slow sellers than from the fast sellers. But even if we have learned everything about the slow seller, say now we have observed the red t-shirt for many, many years, we know on average it sells once a day. Then a Poisson distribution reveals quite little about what will happen on a given day. So that's again the Poisson distribution for a rate of 1. And I have also drawn the binomial distribution for n equal 10 as a comparison. So you can think about this. You have like 10 customers and each of them has a probability of 10% to buy a red t-shirt. Now it's quite likely, or not unlikely, that nobody buys any t-shirt that you have 0 sales. And 0 is 100% off, relatively speaking, from 1. So I have a huge probability to be very off. I also have a huge probability to be more than plus 100% off, because maybe out of these 10 customers, you have 2 that would like to buy a t-shirt, or even 3. It's not so unlikely. This is very different from popular dress that sells 20 times a day. I mean, here, the probability to sell 0 dresses is negligible, and so is the probability to sell more than 40 dresses. You can think about this like having 40 customers and each of them have a probability of 50% to buy the dress. So you can be sure the total number of sold dresses will be around 15 to 25 or so, and that's relatively speaking quite close to 20. So this explains why, if we draw the best possible, the achievable relative mean absolute error as a function of the predicted rate, we have this particular shape here that goes down as we increase the rate. So for rate 1, we have to live with a relative mean absolute error of more than 70%. For rate of 4, we have still to live with about 40%, and then only if the rate is about 100, we can expect the relative mean absolute error in the ideal case to be lower than 10%. We also see there's an unachievable region. So if management comes and says, for the slow sellers that sell around once a day, we want a relative mean absolute error of 40%, that would be that point here, the answer is simply that's impossible if you have a Poisson distributed quantity. And when you judge how well a forecast is doing, you shouldn't measure the distance from the bottom here, from the 0 line, but somehow the distance from that red line. And so you would judge this more or less like I insinuated here with these colors. So by now you have hopefully convinced management that forecast precision will be worse for the slow sellers, but then they come with an evaluation and they tell you, well, but you under forecast the fast sellers and you over forecast the slow sellers. There's a big problem. Well, you will ask for the data and it will give you this table here. So by the observed sales frequency, slow, medium, and fast, they have aggregated the mean observed sales to be 0.8, 5.1, or 13.88, and the mean predicted rate in the same bucket, which is 1.37, 4.6, or 11.0. And obviously, that number is larger than this one. Let's assume it's statistically significant. So we have had many, many days and many, many sales. And that number is much smaller than this number here. And you will go and you will do an analysis and you will come back to management and say, that's totally fine. That's okay. And that's expected. Well, you'll probably have to corroborate that statement a little bit, and I'll give you 3 arguments why that is the case. The first one will be based on Bayes' rule. The expectation that we are having from that table that these numbers should match is simply wrong. We shouldn't expect this to be the case. We just can't expect it. The second argument is just a numerical experiment. You can very easily reproduce this effect with a few lines of Python code. And the third argument would be evaluation hygiene. We are committing a really bad sin here in the evaluation, and we'll see which one it is. So let's start with arguing via Bayes' rule. So what do we actually get from our prediction. Our prediction is a statement about how the sales will be distributed if we issue a certain rate as our prediction. And yeah, I just wrote down the Poisson distribution. You can now compute the expectation value of the sales provided a certain rate. You can plug in these numbers and you find it coincides with the rate. So given a sales forecast, given a rate, the mean observed sales, they should approach the predicted rate in a statistical limit. This is what the forecast is promising you. Now on that table, we didn't bucket by rate, we didn't bucket by forecast, but we bucketed by actual. We bucketed by the actual sales. So what we're interested in is not this conditional probability here, sales given rate, but we are interested in the rate given the sales. So what should we have predicted given a certain sales number? Now, Bayes' rule tells us that these two quantities are related, they're proportional, but we have these two probabilities here that will correct that. Now, if we had a deterministic forecast, then P of rate and P of sales will be the same and they would just cancel out and everything would be fine, but we have a probabilistic forecast. So this will in general not be the same. You can compute the expectation value of the rate given the sales. So what should we have predicted on average given a certain sale? That's an integral here that can be solved analytically for some edge cases or numerically. That's actually not a big problem. And you find that for probabilistic forecasts, in the vast majority of cases, this expectation value does not become the sales value. So given a certain observed sales value, we cannot expect that our mean predicted rate would match that sales value. This is simply not something that's in the box when you get a forecast. The easiest way to see why that has to be the case is consider the sales of 0. So you picked all the days when the t-shirt was sold 0 times. There will definitely be days where you have predicted the t-shirt to be sold maybe half a time or once, and you were just a little bit unlucky that it never sold. So we are somehow post-selecting the bad luck events. So our rate that we will have predicted for these 0 sales is on average definitely larger than 0 because we have never predicted some negative rate. Okay, now we have a slide here with lots of formulas. Maybe your management can be convinced by that, but maybe it can't. And then you can maybe do this numerical experiment here. So let's simulate the situation by brute force. Let's generate lots of random rates, pick them out of the gamma distribution, and let's draw observations again from a Poisson distribution from these random rates. So the rates are distributed like this. Here we have a histogram, and we can then define the masks just as they have been defined for this table. We have the mask for the slow sellers, for the mid sellers, and for the fast sellers, and we mask on the actually drawn observations. So here we have a histogram of the observed sales. We have the slow sellers, the mid sellers, and the fast sellers. And we can now reproduce what we have seen in the table. For each of these masks, we compute a mean predicted rate and a mean observed sales, and you see that these numbers exactly match. So this apparent over-prediction of slow sellers and under-prediction of fast sellers is reproduced one by one by an idealized numerical lab experiment. So it cannot be considered a flaw. I mean, this is all idealized. I mean, the Poisson distribution from SciPy studs works. So this is not something that is broken in the forecast, but it's something that's broken in the evaluation. Now, what's the problem here in the evaluation? Now, we have grouped the results by the actually observed sales, but this is a criterion that is ex post. That was unknown at the moment of the forecast. So this is inadmissible very much in general. This is the very hindsight paradox that you knew better what would happen and you're using future information to group the predictions and the observations. And so you can really say that you should not have known better if you're using something for the evaluation that was not known at the moment of the prediction. Yeah, hopefully you convinced management, but then they will want some solution. How shall we then evaluate? And it's quite easy. Don't group by the outcome, but group by prediction. Then you get a table like this one. We again have the slow sellers, the medium sellers, and the fast sellers, but the predicted slow sellers, medium sellers, and fast sellers. And now the mean observed sales and mean predicted sales will not differ statistically significantly if your model is correct. So, and this is past information. I mean, this is what you know at the moment of the prediction. You can already define the buckets and see, where the sales will fall in. When you do this in Python, it's very similar to what we saw before, but we now have a mask that applies to the rates and not to the actual outcomes. And here all the numbers match quite nicely. And this is exactly what a forecast is promising you, that the expectation value of the sales given a rate will approach the rate. So we went on quite a long journey from what's the forecast mean absolute error to how to judge a forecast and how to see is a forecast a good forecast or a bad forecast. Let me make one more point here. How good is the forecast is just a special case of a much more general question. How good is technology X? Because every technology is constrained by logical or physical bounds. I mean, think if you were not a data scientist, but a rocket scientist. You cannot just have any possible trajectory of a rocket because you're constrained by classical mechanics. I mean, there are simply things that are impossible in rocket science. If you put solar cells onto your roof or you run a power plant, thermodynamics will put an upper bound on the efficiency that you can achieve. And I mean, you can try to argue against nature, but it won't work. And very much like this, we are now here talking about information technology, and that technology is also bound, and counting statistics will bind the precision of a forecast that can be achieved, and this should be taken into account when that forecast is evaluated. So we saw 3 different things that can go wrong when evaluating forecasts. Of course, there are many more. And the very general advice that I can give is a very old-fashioned one, not very original, just test. Don't rely on what you hope your evaluation will achieve. I mean, you don't rely on what you hope your code will achieve either, but you write tests. And don't test it just technically, that if you plug numbers in, you get numbers out, but test it functionally. So build controlled cases of what could happen. Use the ideal case. Use a biased case. Say you're 10% off, you're 20%, 30% off. What would that evaluation tell you? Use some noisy or more imprecise observations instead of the ideal ones. Add some outliers, use a different distribution, and see how that evaluation pipeline will behave and whether it's giving the right answers, because for these test cases, you know the right answers. And when you then understand your evaluation in this lab-like environment, you can also expect it to work out there in the field and to draw the correct conclusions about which model is better and which one then to choose in production. Yeah, I hope you enjoyed this talk. If you have questions, comments, I think we have a little bit of time left, and otherwise we can have a discussion on the talks channel on Slack. Thank you very much.
Thanks, Malte. So we have 2 questions at the moment at the Q&A session. The first question is related to a slow mover forecast. Sammy asks, so can we say that it is hard to forecast individual slow mover forecasts because of they should obey Poisson distribution?
Exactly. That's how I would phrase it. Like the best that I can expect when I predict a product to be sold is in many cases the Poisson distribution. So the best I will get is a Poisson distribution. And here I just have to live with a certain level of relative mean absolute error. And that level will be higher than for a fast seller. So I would, yeah, I would agree with that statement.
Okay, and I think there's Christine has one more question. How do you scale this analysis? And retailers have usually more than 2 products.
Yeah. So the retailers that I work with, they have 10,000s of products, of course. Yeah. So for simplicity, I just only talked about red T-shirts. Yeah. In practice, you will have the dimension of time. So you have 1 T-shirt in time, and you want to predict how that is changing in time. And in addition, you will have the product dimension. On a given day, you have maybe 100,000 different products, and you will have to judge how these products are doing. But the general statistical behavior of your forecast, you can just aggregate over the products. So you can also pick all the products that you predicted to sell about 5 times today, and see how are the real sales distributed across these products. Because once you find maybe some bias, you want to know, is this a product dependent bias? Are you maybe over forecasting all the t-shirts and under forecasting the vegetables? But you can, I was focusing on the statistical part. The individual predictions and observations that will enter, they can also come from different products, from different locations, etc.
Thanks, Malte. So now let's move on to the next presentation. Thank you very much again.
Yeah, thanks.